Welcome to this module of a CSC Masterclass in Fisheries Economics. Hi, my name is Klaas Hartmann. I work in the Institute for Marine and Antarctic Studies at the University of Tasmania. My main role involves bioeconomic modelling of a range of different fisheries around Tasmania. In this role, I'm passionate about communicating my results to industry and management to help inform good decision making. By the end of this module on putting economics into fisheries decision making, you will be able to explain how open access to common pool fish stocks results in a tragic outcome and list alternative property regime, understand the role of bioeconomic models in fisheries management and explain why economists favour a management goal of maximising economic yield, formulate the fisheries management problem as one of intertemporal optimisation and interprets its solution, explain how bioeconomic models can be used to support stock rebuilding, and understand some of the challenges with designing effective fisheries policy. The module covers 6 topic areas. Self-assessment checkpoints help test your understanding throughout the module. Solutions to checkpoint questions are available at the end of the module. In the module on economic thinking, we define the characteristics of a common pool resource, of which fish in the water are an example. Common pool resources are rivalrous in consumption and non-excludable. That is, a ton of fish caught by one fisher cannot also be caught by another, and it is difficult to prevent people from catching fish. Historically, common pool fish stocks have often been available or open for anyone to access as they wish. The results of open access are well known and have been observed in many fisheries. These results include too many resources, capital, materials, fuel, labour, chasing too few fish, with stocks sometimes driven to very low levels, and low economic returns. In essence, a wasteful race to fish, aptly dubbed the tragedy of open access. So why do individual fishers in open access continue to devote more resources to fishing, even when the negative impacts or externalities for other fishers and for future fishers outweigh the benefits to them? The explanation is that no single fisher is motivated to invest in the fish stock by showing restraint today, because they believe correctly that they will not be the one to enjoy the benefit of such restraint. But open access is not the inevitable outcome for common pool resources, and alternative property institutions exist. Firstly, while quite limited in its applicability, private property is not an impossibility. Secondly, many types of communal property arrangements where rights and obligations are vested in a group of individuals are possible. And thirdly, state or public property is an option. The creation of the 200-mile exclusive economic zone effectively made the state the legal owner or custodian of fish resources, and in Australia, at least, it is the responsibility of the state, in this case the Commonwealth and state governments, to decide the terms on which access to fish populations is permitted, and to ensure the existence of the required institutions and rules. A key element to fishery management is to decide on the total allowable catch, or TAC. That is, the total level of periodic harvest that is permitted, usually defined for a particular stock for a year or a season. Bioeconomic models can play an important role in the TAC setting process. Bioeconomic models combine the biological and economic aspects of a fishery to explain stock, catch, effort, and profit dynamics under different management regimes. They can be very simple or complex and can incorporate management feedbacks. The important thing is that a bioeconomic model adequately captures the fishery for the current purpose of management. Bioeconomic models in fisheries have a role in both optimisation and simulation. Optimisation models let us find out what the fishery should look like to best achieve the objectives of fisheries management. Simulation models are used if we want to know the effects on important measures of fishing performance that a particular management change to a fishery would have. Let's begin with the key management problem of setting the TAC and associated biomass or stock level and the level of fishing effort. Economists have generally argued that the objective of management in this process should be to set the TAC that maximises the economic yield, or MEY, of the fishery. Another name for this economic yield is resource rent. Now, there may be some debate about whether there are other economic benefits that should also be considered, and also about whether this economic surplus should stay with fishers as profit or be captured by the state on behalf of the public owner of the fish resource through the sale of fishing rights or using resource rent charges. Now, while there may be some debate about this, maximising economic rent means that we have the opportunity for the fish resource to make the greatest possible contribution to the overall welfare of society. However simple or fancy, all bioeconomic models comprise linked biological and economic subsystems. In this module, we leap straight in at the deep end, leaving much of the detail of how these subsystems might be modelled to the next module. On the biological side, we assume a density-dependent stock growth relationship for a single species represented as a surplus production model. On the human economic side, we specify a harvest relationship where the amount of fish caught is related to both the level of fishing effort and the stock level. It is usual to also assume that there are diminishing returns to effort. That is, for a given stock level, successive increases in effort will increase harvest, but at a declining rate. This is a common assumption in economics for many production processes. It is also usual to assume that there is a stock externality effect. That is, for a given level of fishing effort, the harvest will be higher at larger stock levels. We can formally state the management objective as choose a level of catch and thereby effort in stock that maximises the net present value of the net benefits, economic rent, that we get from the fishery, subject to 3 constraints. Now, the first 2 constraints make sure that the solution to this problem is feasible, both biologically and economically. The third constraint ensures that we harvest only the surplus production or growth increment of the stock in each period. This restricts us to solutions that involve a constant harvest each period and result in a stable stock level. If we don't add the sustainable yield constraint, our optimization might give us a bang-bang solution, which economists recognise is not likely to be optimal once we account for other economic, biological, and social considerations. Solving the optimization problem provides management with a rule for setting the long-run TAC in the fishery, when the objective is to maximise the value of the fish stock. That is, set the TAC at the level of sustainable harvest achievable at the biomass where the rate of return on holding additional fish in the water equals the rate of return on money in the bank. We can see the logic of this by asking, what if this condition didn't hold? If it isn't the case that at the current biomass level, the rate of return on holding additional fish in the water equals the rate of return on money in the bank, then you could always increase the value of the fishery by either holding less wealth in the form of biomass in the fish bank and more in the money bank, or vice versa. This way of looking at the problem treats fish stock in the same way as an investor would treat any other form of productive asset. And the rule above is just a specific case of a general condition for socially optimal intertemporal resource allocation. When the aim is to maximise the return to a portfolio of productive assets, fish in the water included, then the best thing to do is to equate the return from the last dollar spent on each type of asset. The idea of fish in the water earning a rate of return may need further explanation, and there are 3 ways that this may happen. When an extra tonne of fish stock is kept in the water, rather than landed, it reduces the marginal cost of fishing. This occurs because the catch rate, or catch per unit effort, CPUE, is higher at higher stock levels, as captured in the harvest relationship described earlier. We call this the stock externality effect. Leaving an extra tonne of fish in the water also changes the periodic growth increment in the fishery. As the surplus production relationship shows, this biological return may be positive, negative, or 0 depending on the current stock level. This is called the marginal stock effect. A tonne of fish left in the water, lastly, can either increase or decrease in value due to changes in prices and or costs of fish stocks over time. This is called the capital gains effect. Here we show the rule for identifying the efficient level of biomass graphically, assuming that there is a constant real price of fish and cost of effort over time, so that there's no capital gains effect. In this figure, the rate of return on alternative assets, as represented by the return to wealth held in the money bank, is constant, while the rate of return on fish in the water declines as the biomass increases. This reflects the declining marginal stock effect or biological return, with the curve sitting further to the right for fisheries where the stock externality is stronger. So what conclusion can we draw about the relationship between a management objective of MEY and the well-known alternative of maximising sustainable yield, MSY, in terms of key fisheries variables, harvest, biomass, effort, economic yield? The result of this comparison is summarised here. Not surprisingly, harvest will be higher under MSY and rent higher under MEY. Note though that the relationship between the long-run optimal biomass and effort levels is ambiguous and depends on the relative strength of the two driving economic imperatives in the intertemporal optimization problem. That is, the imperative to keep higher stock levels to increase CPUE and reduce costs versus the imperative to fish harder now due to the opportunity cost in terms of foregone returns in other economic activities. It is hardly surprising then that these results have sparked much discussion. For example, about the possibility that extinction might be an economically optimal outcome, and of course about what the appropriate rate of discount should be in problems involving the use of natural resources. While we do not discuss these further here, we have included references to readings on both issues at the end of the module. So far, we have talked about bioeconomic models as a way of informing managers about how catch should be regulated in the long run. In this module, we leapt in at the deep end and formulated the management problem in a way that accounted for the fact that fish stocks provide net benefits over time and that decisions made today have repercussions for stocks and fishes in the future. We return to a slightly simpler version of the same management problem in the next module, in the form of a static bioeconomic model, as preparation for the hands-on management simulations that follow. It is worth noting, however, the growing role for bioeconomics in informing fishery stock rebuilding strategies. That is, strategies aimed at increasing the level of fish biomass, say to its MEY target level. Rebuilding, of course, requires reducing current harvests below the level of surplus production in order to increase biomass. Ceasing harvest completely would achieve rebuilding to the target level in the shortest time possible, while more modest reductions in harvest would achieve the target over a longer period. Dynamic bioeconomic models can be used to help managers understand and balance the risks to fishery stocks against the economic risks to fishes, processors, and the communities that depend on their activities for alternative transition pathways. As an example, these authors use a dynamic bioeconomic model to solve for both the MEY biomass target and the optimal transition path. Their findings show that the value of the fishery under a business as usual policy is more than $3.4 billion less in present value than when managed to a MEY target. Notably, the fishery has a positive long-term net economic return with MEY, which does not occur with the business as usual policy. However, compared with the base case business as usual strategy, the authors predicted 42% less employment during the optimal transition to MEY and 18% less employment in the long-run MEY equilibrium for Pacific Island countries. Thinking as an economist, the key question, and the one that the policymakers should be informed of, is what is the opportunity cost of each of the extra jobs if we stick to business as usual? According to this work, the cost, in terms of foregone economic rent at the long-run equilibrium, is a staggering $1.34 million per job. The magnitude of this cost suggests that those who are made redundant could be compensated for their losses and retrained, and there would still be some gains left over to meet one of society's many other needs. Our final task in this module is to ask the question, how do we get fishers to behave in a way that is consistent with achieving sustainable MEY? That is, how do we get them to catch the right amount of fish at minimum cost? The answer lies in having the right incentives, regulations, and institutions in place to align individual behaviour with the collective good. Achieving this is complex, and it is an area that economists and fisheries managers are still learning about. Historical experience is, however, replete with examples of attempts to do this that have not been entirely successful and have left managers surprised. For example, early attempts to control catch by restricting the use of fishing inputs, or effort, led to effort creep as fishers substituted uncontrolled inputs for controlled inputs. In this example, limits on vessel A units, a measure of hull capacity and engine power, led to substitution toward unregulated gear head rope length. We can tell that this must be an inefficient substitution, since fishers would have chosen this combination of inputs before the regulation if it had been more cost effective. Now, even if controls and effort could be designed to effectively restrict harvest to its target level, there will be a loss of efficiency and rent dissipation. Rent dissipation means that any surplus value created in the fishery is used to support inefficient fishing practices and is therefore not available to benefit the greater community by doing things like reducing national debt or improving our hospital system. History has also shown that imposing a TAC restriction alone will not curtail the race to fish that made open access a tragedy. In this case, the race will manifest as capital stuffing, as individual fishers overinvest in boats, gear and other equipment. The result, overcapacity and economic rent dissipation. The implementation of tradable catch shares, called individual transferable quotas or ITQs in Australia, is a more recent attempt to align individual behaviour with the collective good. ITQs are sometimes called quasi-property rights, as they establish a property right in a share of the TAC, not in the fish stock, ownership of which remains with the state. It is suggested that together the combination of establishing a property interest in the fishery and the tradability of this property interest through quota markets means that fishers will have an incentive to be better stewards of the resource and that the TAC will be caught at minimum cost, thereby maximising the rent generated by the fish stock. While there have been benefits as a result of ITQ management in fisheries, it is becoming clear that the anticipated benefits are easily compromised and that their design is challenging. We have included several readings at the end of the module that highlight these problems and begin to address the challenges.